Lab 7, obviously. Two parts, both of which use this apparatus over here. Maybe I'll leave the camera there for just another moment and hope that's the thing that shows up at the, when you click on it. We have over here a vacuum tube. And the way it worked, well, if you were actually doing this lab itself, the first step would be to connect all these wires that I've already got connected here. It would probably be a good thing to go over it though, one wire at a time, because you kind of see how it works in the process. So first of all, vacuum tube technology is kind of an outgrowth of light bulb technology in a way. Most vacuum tubes involve manipulating a beam of electrons. And as I discussed earlier in class, where the electrons come from is they're emitted by a hot filament. So you won't actually be able to see the filament glowing because it's back up in here where the view is kind of blocked. But the first step is to get that filament hot, very similar to the filament in a light bulb that you would just use, well, an old-fashioned light bulb, an incandescent light bulb. That's what these two wires here do, okay? I don't know if you can get close enough to read that, but that says 0 volts, and this says 6 volts, 4 amps. Well, exactly how many amps you get would depend on the resistance that you connect it to, but that's probably the maximum. Alternating current. So low voltage, relatively high current, and those wires plug into the back of the tube here. And it just, the current goes in there and heats up the filament and returns to ground, except it's an alternating current, so it actually goes back and forth. But that's that part of it. So getting the filament hot makes electrons cook off of the surface of the metal in a process very much like evaporation of a liquid, okay? If you're boiling water, you have to get the water warm enough to boil, and at that temperature, the water molecules are moving around fast enough that they can escape from the surface of the water and become a gas. And in a kind of an analogous way, you get the filament hot enough and the electrons inside of it gain enough energy to escape into the surrounding empty space. So now you've got all these electrons floating around in here. The reason they call it a vacuum tube, of course, is that all the air has been pumped out because the air molecules would get in the way otherwise. Well, then you can see there's some hardware over in here, and over there on the other side, you see there's a wire connector that passes out through the glass, and I've stuck a wire on it, and this is that wire here. It goes to this. See, the power supply is putting out two separate things. It puts out the low voltage alternating current over here for the filament. And between here and here, we have a high voltage that we can control with these knobs. And exactly how many volts can be read off this meter here. And that's the accelerating voltage, okay? This metal hardware over here gets charged up positive with a potential difference of several thousand volts. That produces a fairly strong electric field that grabs those electrons and pulls on them and gets them moving fast. And I don't know if I can get the proper angle here to see inside the tube. Yeah, you can kind of see there, it's blurry. But there's a slot in the end of the electrode there. Can I make it focus any better? No, I think it wants to focus on the surface of the glass rather than the stuff that's inside of it. Well, anyhow, even though it doesn't show up very well, there's a horizontal slot in the end of that electrode. Beams, or an electron beam comes shooting out of there. And then this screen is coated with a fluorescent material, or is it phosphorescent? I'm supposed to know this stuff. I'm the professor. Anyhow, whatever the right word is, when an electron crashes into that material, what used to be the kinetic energy of the electron before the collision excites the molecules of the phosphor, and when the molecules return to their ground state, they give off light. So we can see where the electrons are hitting the screen, which shows us the path of the electrons, kind of like that. Okay, that blue line across there shows us the path that the electrons are following through the tube. It's very similar technology to an old-fashioned TV picture tube, except in that case, the phosphor would be painted on the end instead of in a little screen that's been stuck in the interior of the tube. So that's what's going on with the tube. We have this other power supply over here, and that supplies power to these magnets, these so-called Helmholtz coils that are around the outside of the tube. The more current that we put into these coils, the stronger the magnetic field they will produce. And we can read the current with this meter here. Okay, so current, current comes out of positive, goes through the meter, and of course you have to connect it to the right socket to measure amps and not volts. And then follows this wire, goes into the coil on the back. See, can't see it, but the one on the back looks just like this. It's got two sockets in it to plug wires into. After the current goes around that coil, comes around this wire, goes to this coil. The two coils are in series with each other. And then after going around that coil 320 times, it's written right on there, then it returns down the black wire here, the power supply. So that's the details of our apparatus, and we are ready to begin actually performing the experiment. So I have the directions here. Part 1, the sign of the electron's charge. Okay, the electron was discovered in the closing years of the 19th century. After vacuum technology became available to suck the air out of a tube similar to this one, it became apparent that if you applied a high voltage, that some sort of rays were emitted by the cathode, and they called them cathode rays. The more modern term is to call them electrons, but in the early days, they were called cathode rays. And so what are these cathode rays? How do you figure that out? Well, one thing you might want to do is check them for electric charge. And the way you could do that is to shoot these mysterious rays through, you could use either a magnetic or an electric field. Either one should push on them if they're electrically charged. In our case, we're going to use the magnetic field from these coils. So step 1, connect the tube to the power supply as shown, did that. Step 2, connect the second circuit to the other power supply, did that. Number 3, turn on the tube's power supply set for between 2,000 and 5,000 volts. Yeah, I've got it almost full throttle here. Just don't have to be too precise about things at this point, but that's just under 5,000 volts. And You know, actually, the beam might show up a little better if I turn out some of the lights in this room. Didn't want to turn them all out because then I couldn't like read the directions or anything. I don't know if that helped any, but it didn't hurt. You can see the beam pretty clearly on the monitor. The blue line you see is the beam's path. Send some current through the coils. Okay, so flip the switch and notice that the beam that's shot out of the gun horizontally no longer goes across the screen horizontally. Actually, just a second. I turned out the rest of the lights in the room. Can still see well enough, and it makes the beam show up a lot nicer. So send some current through the coils. And like I said, I can control the current by turning the knob on the power supply. More current makes a stronger field. Less current makes a weaker field. And what does it say to do next? If there is little effect on the beam, then yeah, what happens sometimes is the students wire this up so that the two coils create fields that point in opposite directions. And this is just saying that if it doesn't seem to be working, switch the wires on one of the coils. To observe whether the beam is positive or negative, to see the direction of the field B, hold a magnetic compass just outside the tube. Got the compass here. Camera there, it shows. The blue end of that compass points north. Okay, you can see that, well, I don't know if that actually helps any, but the end of the room with the blackboard in it is the north end, the end toward the throughway. And it's the blue end of the compass that's pointing in that direction. So I bring it over into here where it's in the field of the coils. And well, when I get it off to the side, you know, it points a little bit one way or the other. Right in the center of the screen, it goes right through along the axis. But that illustrates that the magnetic field points horizontally away from you, more or less perpendicular to the screen. Okay, so the B vector points that way. The velocity of the electrons, the B vector, well, that just comes from understanding how the tube works. The electrons are being shot out of this gun back here. It shoots them in that direction. So again, B that way, V that way, and the electrons are clearly being pushed that way, upward. So like I said in class, well, the recordings of the class, in magnetism, everything's perpendicular to everything else, okay? V is, well, it doesn't have to be perpendicular. Everything doesn't have to be perpendicular, but in this case it is. Velocity of the electrons, the direction of the magnetic field, the force on the electrons pushes them upward. So what you need to do is, and the answer sheet has some space for you to draw little pictures showing, you know, X's or dots for the direction of things that are perpendicular to the page, and arrows for any vectors that lie in the plane of the page. You're supposed to illustrate all of these directions, look at them, apply the right-hand rule, and figure out what is the direction of V cross B. See, the force on a charged particle, like these electrons, equals Q times V cross B. So figure out the direction of V cross B. If that's the same as the direction of the force, then Q is a positive number. If V cross B and the force have opposite directions, then that means Q is a negative number. And that's how you're going to figure out from this observation here whether so-called cathode rays, electrons as we would call them today, that's how you're going to figure out whether they're positive or negative. Clearly they're not neutral, or the beam would just go straight across no matter how strong I turned up my magnetic field. So plus or minus, you figure that out from what I was just saying. And that is part one, which is the shorter part of the experiment. Part two is a kind of shortened, simplified version of the experiment J.J. Thomson did in 1897 it was the original discovery of the electron. What Thomson did is he used a setup kind of like this one to determine the charge to mass ratio, E over M, or Q over M, whichever letter you care to use for the charge of the electron. Since the beam had this clearly defined ratio of charge to mass, that very strongly suggested it was made up of a bunch of individual particles. You wouldn't expect something continuous to behave that way necessarily. And so that was, the first discovery of an elementary particle. E and M, the charge and mass of the electron, did not become known individually until about 10 years later, when Robert Millikan did his oil drop experiment that you already looked at back in lab number 3. Although in the late 1800s, the value of the charge was suspected as being the same as that of a hydrogen ion. Nobody'd actually succeeded in definitively measuring it yet. So at this point in history, you aren't finding E and M individually, but you were able to find the combination E over M. And then 10 years later, once you know the charge of the electron, then this experiment would tell you its mass. Anyhow, procedure. We need the diameter and separation of the coils. I'm going to turn the lights back on for a moment. Actually, I'm going to give the tube a rest also. Like anything else, the more you run it, the quicker it wears out. Let's see. I thought I had a ruler here, but I guess I don't. Okay. D for diameter. We need the diameter of the coils. Of course, you've got one layer of wire wrapped on top of another, wrapped on top of another, wrapped on top of another. We need sort of an average radius. And so that would be center to center. But, well, it's kind of hard to judge by eye exactly where the center is. If you went left side to left side, or if you went right side to right side, that would be the same as center to center and much more well-defined and easier to read off of a ruler. Also, easier to read off of a ruler, since we're only using one setup. This would exactly be an option, and I've got a whole class running here, but I grabbed a spare coil because the tube is kind of in the way to try and measure it there. So you know what, that kind of falls off. I'm going to put the edge at the 10 mark instead of the 0 mark. And hopefully I'm running that across. I'm kind of judging a diameter by eye here. You don't want to be off center or comes out a little short that way. Well, we're going to go with that. So as I said, I've got this side of the coil lined up on the 10 centimeter mark. And then over here, now we've got to remember to subtract off that 10. And remember, you're looking at the inside. We're going to go left side to left side. So we want the inside edge, not the outside edge. And if I get it where you're looking right straight down at it, I want to call that, after subtracting off the 10, well, it's either 13.7 or 13.8. If you wanted, it's right in the middle. Well, when you can't make up your mind, why not just call it 13.75? I'm going to write that down. Okay. We also need the separation of the coils, the two, how far they are from each other. This is complicated somewhat by the fact that they're not exactly parallel to each other. I mean, they're fairly close, but there's a few millimeters difference typically. The other thing it's complicated by is that these things aren't exactly welded in place. They can kind of move around a little bit. So it's kind of important to measure these last thing before starting to take measurements, as in after you've measured the separation, don't touch them again, because you might move them and mess up your results that way. So trying to be gentle in my handling of them. See what I'm going to measure on this side, and then I'm going to measure over here on the back side, and we'll average, okay? So I'm going to go once again left side to left side, and I guess I might as well just line it up like that. And I'm kind of debating between 7 and 7.1 there. Well, let's go with 7.1 centimeters. I don't know if that showed up, probably not, but for the back, the thing is, you know, trying to get the ruler in there, which you kind of can. You can get a fairly good idea, but what strikes me as a little better is I've got a pair of dividers here, which for those of you who have grown up in the world of computer-aided drafting, maybe you've never even done any drafting, but this is traditionally, back in the days of manual drafting, something you would use for mechanical drawing. But it's also handy for, oh, that's the ammeter telling me it's been left on for here. Just take a rest. See, I can fish it down in there and then get the points the right distance apart. And that looks like it's pretty close, because I'd already adjusted this before I started the video. Yeah, I think you can change how far apart that's in front of the camera. You turn this little screw over here and it adjusts how far apart the points are. But I believe I have them the proper distance apart, measuring over here on the back. And we've got get the 1 point on 0 and the other one there again, I don't know, that might be fuzzy. I don't know if you can read it or not, but that's about 7.6. So 7.1 on the one side, 7.6 on the other side. Average those, that would be what, 7.35? I just did that in my head, check my math, but that's what we're gonna use for S, the separation center to center between those coils, okay? And where are we in the directions? Turn on the tube, leaving the field off. Ah, yes. Now, what this next part is about is that I'm not completely sure, but I kind of think that these tubes are handmade. I mean, it's not exactly a huge volume production kind of thing. And the screens don't all seem to be placed in exactly the right spot in all of them, which shows up a little better in the horizontal position. I'm going to turn the lights back off again. So basically what this next step is saying is to pay attention to what the beam looks like with the magnetic field off, okay? You can see the power supply over it. The little red light is not on. When it's on, it looks like that. So no current coming from the power supply. And see how, I don't know if I can make this show up clearly or not. Yeah, that looks pretty. Over in the area of X equals 8 or 9, where we're going to be taking our data, notice that in this particular tube, the beam actually runs, you know, the beam is supposed to be shot right down the x-axis in a perfect world. But in fact, there's a little gap, maybe not quite half of a division. And it's fuzzing up, but it was pretty clear a moment ago. If you want a better look at it, just back up the video. So, you know, in some of the tubes, the center of the beam goes along the axis real nice. In others, it's the bottom of the beam or the top of the beam. On this one, it's misaligned enough that there's actually a little bit of a gap, which means we need to read a little bit below the bottom of the beam when taking the data, okay? We need to read the position where the x-axis relative to the beam, you know, where we need the position where the x-axis would be with the field off to correct for the fact that apparently in this particular tube, they got the screen a little lower. Either that or they mounted the gun a little higher than would have happened in a perfect world. Now, judging how far out of place it is right to left is a little bit trickier. If you read through the directions, you'll see that for some of the tubes, there's a little bit of a correction that needs to be made for that also, which I've determined in a couple of different ways for some of these tubes. I put a little tag on each tube here at the back. And this one, I've got all 6 tubes there. I might as well grab one where it's no correction needed. So in this video, there's 2 columns on the answer sheet. If I can figure out where I put my answer sheet. There's a column that says X, And then there's a column that says corrected X. And for this particular tube, those will be the same thing. In fact, if you just want to leave the corrected X blank, we aren't going to use it for anything. But, you know, when we run this lab in person, there's several of the tubes where you would have to add or subtract a few millimeters to correct for the horizontal position of the screen. So that's what that's all about. Okay, so introductory comments taken care of, I guess. Back to the directions. So around x equals 8 or 9, notice where the x-axis is relative to the beam. And as I said, for this particular tube, it's a short distance below the bottom of the beam. Step 3, turn on the magnetic field. From the centimeter grid, record the x and y coordinates of a point on the beam somewhere around x equals 8 or x equals 9. So there's the field. And I'm going to, kind of nice to have a round number. I'm going to adjust the accelerating voltage a little bit. So over here on the power, see there's a coarse adjustment and a fine adjustment. I just need to change it a little bit. So I'm going to change the fine adjustment knob. And apparently I need to change this one also. Okay. So to the extent we can trust this meter, that's exactly 5,000 volts. And it seems though I've cross-checked it against, at least on one or two of these power supplies, cross-checked it against another meter at some point in the past, and there wasn't any problem. So, oh, that's static electricity. There's apparently some charge accumulating on either on my fingers or on the glass that I'm disturbing, and that would seem to indicate I shouldn't do that. Anyhow, I'm going to go for the point x equals 9, y equals 2. So back off on this just a little bit. And of course, it's always just a little too much or not quite enough. But I think maybe right about there, you probably, well, maybe just a little bit stronger. And I'm going to go for that. Okay. I don't know if you can see the grid lines from where you are, but oh yeah, that snapped into focus for a moment there and then fuzzed up again. But x equals 9 and then y equals 2. That point is just a short distance below the beam, just like the x-axis was that short distance below the beam when the field was off. So aside from, okay, accelerating voltage, 5,000 volts, I already showed you that. X equals 9, Y equals 2, and you also, oh, be a good idea if I had the ammeter turned on. There's the current in the coils, 0.275 of an amp. Well, I paused for a little while there to run through the calculations just to make sure everything was working out all right. And at least for that first trial, that's giving a pretty good result. So if you're not getting a good result, it's not the numbers. Common mistakes. Well, for one thing, forgetting to convert centimeters into meters when you calculate R or elsewhere. As usual, if it's not working, send me what you've got and I'll figure it out for you. We need to do 2 more trials. So we'll just kind of shuffle around for different accelerating voltages and different currents and so on, and get 3 trials that we can average. So having done one at 5,000 volts, and that's kind of slanty, I'm going to do the next one at 4,000 volts. Now, if you go down too far, the problem is the lower the voltage, the fainter the beam gets, but you can still see it pretty clearly at 4,000. So that's the voltage for the next trial. And then instead of the 0.92, maybe it would be fun to have the 0.91 this time. Again, just a little bit, like about a half a box below the bottom of that beam. Of course, I've got a third of a box when I wanted a half a box, but you turn the knob and then it goes too far the other way. So, well, that's what experimental uncertainties are for, among other things, I guess. So probably right about there. So we're going to go with this point over here. And I touched the glass again. Approximately 9.1. X equals 9, Y equals 1. And the current that produces the right magnetic field to go through that point looks like it's 0.128 of an amp. And actually, I could probably get more decimal places if I switched it to milliamps, but that's all right. So I'm not going to bother running through the calculation. Maybe I should at least write it down. That was 0.128, 4,000, 0.128. Oh, by the way, there isn't a blank for this on the answer sheet, but you do need, I pointed it out once before. It doesn't really show up with the lights out, but it's written on the coil right there where you can't see it, that N, the number of loops in each coil, is 320. You need that as part of how you calculate the magnetic field. So, you know, how many Teslas. So we've got V, we've got I up to the 0.91 this time, and one more trial. Let's turn it down a little more. Like I said, I don't want to go too far down because then the beam starts getting faint and hard to see, but maybe 3,500. Well, looks like it's pretty much on the mark there. And again, variety is the spice of life. Let's go for the 0.82. A little further. Yeah, I think I like that. Okay, so there's X and Y there. X equals 8, Y equals 2. The current producing the magnetic field this time, well, it changed. Slightly unstable. All else being equal, I'm thinking 0.29 is easier to punch into a calculator than 291 or 289. So I'm going to write down 0.290 of an amp. And I believe we now have, yes, you can go to sleep now. I believe we now have all of the data. The rest is calculations. You'll need to show how to derive the expression for Q over M. There are two different things you have to put together. One is the idea that since the electrons are moving along a circular arc at a constant speed, anything in uniform circular motion has to experience a central force equal to mv squared over r. In this case, that's provided by the magnetic force, which is equal to qvb. And so that's one thing. QVB has to equal mv squared over r. But aside from Q over M, okay, you're not going to solve individually for Q or M. You're going to treat them as a unit. The charge to mass ratio, you're going to pretend it's 1897, and you're trying to determine the charge to mass ratio, just like Thompson did. So you treat Q over M as a unit, and that's what you're going to solve for. Trouble is, the expression I just mentioned contains another variable, which is the velocity of the electrons. You want to be careful not to mix up V for voltage with V for velocity. That's another little pitfall. The way you're going to get not a number, but an expression for the velocity is conservation of energy. And this is identical to an example I did in class in, was it section 2 or section 3? Anyhow, several weeks ago, there was an example in class. There was an extremely similar example in the homework, and you can kind of imitate that the potential energy that the electron has when it first cooks off the filament equals the kinetic energy that it has at the other end of the gun when it's built up to its final speed. So you use that conservation of energy relation to get a substitution for the speed of the electrons that you put into the other equation, and you do some algebra, and at the end of it all, you have an expression Q over M equals an expression that's all stuff you've measured, okay? One common mistake is people have an expression for Q over M that also has a Q and an M on the other side of the equal sign. And they go to their formula sheet and they look up the charge and mass of the electron and they fill it in there. And that's circular reasoning, okay? It's like, you know, if you assume that pi equals 17, then it's really easy to prove pi equals 17 from that. You're not supposed to assume values for the charge and mass of the electron. That's the unknowns that we're dealing with here. So, so don't do that. But you should be able to come down to an expression in terms of the accelerating voltage, the strength of the magnetic field, and the radius of the arc that the electrons are moving along, all of which we have measurements that tell us, okay? So that's probably about as much advice as I can give without just simply giving everything away. And that's this one. See you in the next, no, you'll see me in the next recording.